Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to begin our investigation of hyperbolas centered at the origin. We're going to begin with a couple of examples of a hyperbola that opens left and right. This has what we call a horizontal transverse axis. The transverse axis is that line segment there. A hyperbola is basically, it looks like two parabolas, one opening to the left, one opening to the right. In a later video, we'll do one where it opens up and down. The format of the equation is shown here. X squared over a squared minus y squared over b squared equals 1. And the difference from an ellipse is in that sign, the difference. So when we were subtracting x squared minus y squared, we're going to end up, as long as it can be put in this form, we're going to end up with hyperbolas that open left and right. The vertices we get from a, the number that's being squared underneath the x squared term. And really, the first step could be like when you were graphing an ellipse. So I know A, the number under X, tells me left and right. I know B, the number under Y, tells me up or down. And so if I put those 2 points, A to the right and A to the left, and maybe I add another two that are B up and B down, we can make a rectangle out of those. And the corners of the rectangle along with the center, that's where the asymptotes, which are shown in the red dashed lines, go. And they tell us how the function behaves as you zoom out further and further and further. And so, and maybe I'll show you one of those on Desmos. As we zoom out and out, it looks like a big X, even though it turns inside of there. Maybe we'll show you that before we're done. The definition for a hyperbola is there are two foci as well. And just like with an ellipse, if we pick a point on the hyperbola, the difference between the distances remains the same. So instead of adding the two distances together, we find their difference. So let me just switch colors to show you this. If I pick a point somewhere on the curve, this distance and this distance, the differences between them, ignoring the sign, remains constant. So whether I pick that point or I pick this point, it doesn't matter. Connect to the two foci, subtract the differences, it's going to be the same. The equation for the asymptotes, they'll have, of this type, the slope is going to be y equals b over a, y equals b over ax, or negative b over ax. Finally, to find the foci, we use this equation, c squared equals a squared plus b squared. So that's a little different from what we saw with the ellipse as well. Let's go ahead and try a couple of these that open left and right. Maybe. Here we go. So I'm looking to graph this hyperbola, and I need to get it into the right form. So I'm looking for something like x squared over a squared minus y squared over b squared equals 1, which I don't have yet. But just like with the ellipse, if I divide both sides of the equation by 36 and simplify, it will be in that form. 9 over 36 becomes a 4 in the denominator. So x squared over 4 minus 4 divides into 36, 9 times y squared over 9 equals 1. So I know the center is 0, 0. A squared equals 4, so a equals 2. That means I move 2 to the right and 2 to the left. And I need those as points. That's where those branches of the hyperbolas are going to turn. Now, b squared equals 9, or b equals 3. That's not going to give me a point on the graph, but it's going to give me a form to draw my asymptotes through. So I move up 3 and down 3. And those 4 locations, I can make a rectangle out of those. I'm going to go ahead and do that. And what I know is that the asymptotes have to pass through the corners of that box as well as the center. So the first one goes like that. That is y equals 3/2 x. Now notice I didn't really need to use that slope at all to graph it, but if you look at that point right here, that's up 3/2, just like the slope of the line would have been. So the box is kind of a way to shortcut that procedure, but it still does the same thing. Then we would have one going down at a slope of -3/2. Same idea. Even when we start moving the center around the graph, the asymptotes can still be created the same way. Draw the box, crisscross. Right. We should figure out what c is. C squared equals a squared plus b squared. C squared equals 4 plus 9. C squared equals 13. C equals the square root of 13. So we know that's between 3 and 4. Let's get a value for that. Square root 13, 3.6. So 3.6 to the right and 3.6 to the left. Those are the two foci. And then what I've got to do is draw a parabola that on each side that heads towards those asymptotes. So back to blue. Something like that. And something like that. Now the red dashed lines, the blue dashed lines, they're not actually part of the graph, but we use them as guidelines to help us draw the graph. Let's see. The vertices were at 2, 0 and -2, 0. The foci were at root 13, 0, negative root 13, 0. And remember that we use 3.6 as an approximation for those. The domain, notice as we go from left to right, let's just sneak it down here. The domain, as we go from left to right, it's got arrows pointing to the left, and then it turns around at -2. So that's from -infinity to -2. Union, the second piece, starts at 2 and goes forever to the right, 2, infinity. The range is a set of all real numbers. Notice we have arrows pointing up and down. That means it covers all of those values. Right, so that's our first one. Let's try one more of this type. Here we have x squared over 25 minus y squared equals 1. When we don't see a denominator, remember that it could be a 1. That helps us to see that a squared is 25 and b squared is 1. A is 5 and B is 1 from the two denominators. The center is 0, 0, so let's start with that. The vertices are at -5 and 5 on the x-axis. B is 1, so if we go up 1, and this time I'm going to use a highlighter for this one. Now the asymptotes go through that. So let's draw those in red. And so we can see that going left and right, it's pretty tight in there. So this graph's going to look a lot different than the last one. Through the vertices towards the asymptotes. And let's see, we need the foci. C equals, I'm going to write it like this, the square root of a squared plus b squared. C equals the square root of 25 plus 1, or the square root of 26. Square root 26 is 5.1 approximately. So that's barely past the vertices. You almost wouldn't be able to tell them apart. Foci, root 26, comma 0, which is about 5.1, comma 0, and negative root 26, comma 0, that's about negative 5.1, comma 0. Domain, negative infinity to negative 5, union 5 to infinity, range, all real numbers. Now I mentioned, let's try to graph this one on Desmos so that you can see what this looks like. All right, in Desmos, I have typed the equation for the hyperbola, x squared over 25 minus y squared equals 1. I've also typed the equations for the asymptotes, which I didn't mention when we were on that screen. Y equals 1/5 x b over a, and y equals negative 1/5 x, negative b over a. Those are in the red dotted lines. The hyperbola itself, we can see in the blue. And so let me hide this. And then I wanted to show you what happens as we zoom out. So here we can clearly see, maybe we should zoom in a little bit. Oh, that's not going to help. But we can see the graph of the hyperbola. But if you take a look as you go farther and farther out, that blue line is approaching the red dashed lines. And if we zoom out far enough, you can't really tell the difference between them. And so those x's that we see there, they really guide the behavior of the hyperbola. All right, that's it for this type. In the next video, we'll talk about hyperbolas that open upward and downward instead. And let me get back to the home sides. If I change the signs of these two terms, that's what we get. We'll get a hyperbola that opens upward instead of downward. But the same strategies, notice the asymptotes aren't going to change at all. It's just the asymptotes give you 4 regions, top, bottom, left, right, and you got to figure out which 2 you're going to graph in. All right, that's it. I'll see you in the next video.